So this is a graph of y equals e to the power of minus x squared. So this is your graph here. We are going to revolve it 360 degrees along the y-axis. So when you do that, you're going to get this solid here. So when you revolve it 360 along the y-axis, you're going to get this 3D solid looking something like this. It looks like a 3D hill. It looks like a 3D hill. So our job is to work out the volume of this solid. To do that, well, if you look at this, this thing here will never reach zero. So it will never reach zero. It will never reach zero. So when you try and work out the volume, you can't really integrate it from 0 to 1. You can't really integrate it from 0 to 1. You can't really integrate it from 0 to 1 because dead on 0 it will break down. So we have to do it like this. We have to integrate it from b to 1. So let's call this b, and this is 1 here. So integrate it from b to 1. Integrate it from b to 1, and then later on take the limit as b heads towards 0. As b heads towards 0 from the positive side. So you're heading to. So b is sliding. B is here. And then you slide it towards 0, and then you're approaching 0. B heading to 0. You're approaching it from the positive side. It's not as if you're approaching 0 from the negative side. So you're actually approaching it from the positive side. So that's why you need this approaching 0, and then you've got your plus here from the positive side. Well, anyway, in order for you to work out this solid, I need you to understand the concept of solid of revolution, and we've done this. And I need you to understand integration by parts, and we've done this. And I need you to understand L'Hopital's rule, and we've done this. So in order to work out this solid, you would need all these three components. Okay, and the reason why this is useful is because of this. Hang on. That formula. This equation here, e minus x squared, can be used to model. Let's say you're trying to build a missile to fire at a city. So you're in one country. This is a sea here, and this is another country here. You're trying to design a missile that will fire at a city. So if you look at this here, hang on. This is your x-axis. This is your y-axis. And hang on. So remember, our function looks something like this. So because you're aiming at the city, you're most likely to hit the center. So this is a bird eye view of the whole thing. So this is a sea. This is a sea. The tree is here. The tree is here. Your missile is here. Your city is here. So this is you looking down on it. So this is your x-axis. Up here, this is your x-axis, your y-axis. Here, because you're looking down, you won't be able to see the y-axis. So when you fire a missile, because you're aiming at the city, you hang on. So this is some sort of radius, some sort of radius here. Because you're aiming specifically at the city, you're most likely to hit the city. But sometimes your missile will overshoot somewhere here. So when you're looking at the bird's eye view of it, when you fire your missile, it might hit somewhere around here. But the point is that your frequency graph will look something like this. You're most likely to hit the center because you're aiming towards the city center. You're aiming towards the city center. So there is a chance that the missile will overshoot and hit the next town. Yes, that is a possibility, but the probability of that is really low. So this y equals e to the power minus x squared. You can use this to model a city and work out the probability of it hitting your target. Okay. Well, anyway, let's try and integrate it. So we are trying to integrate this solid. So there are several ways of doing this. We can do it in terms of dx, but let's just do it in terms of y. So we're going to do it like this. So the volume is equal to the integral. So we are going to move along the along the y-axis. You can see we're moving along the y-axis, so it's going to be something dy, because we're moving along in the y-axis. So each step of the way, hang on, so we're moving along like this, because we are moving along in terms of dy, so this is our track of y here. We would need to know the radius here. Once we've got this radius here, we can pi r square it. That will then give us the area of the disk. So we would need to pi r square it. But the thing is, what is the radius here? What is this? This r here is the radius. Once we've got the radius, we can pi r square it, and then that will give us the area of the disk. And we're summing up the disk from B to 1. Let's call this B here. From B to 1. But then what is this radius here? What is this radius in terms of y? So for given y, remember y here could be 0.9. So given 0.9, how would you work out the radius here? Well, you would look at this and make x a subject, because this is x here. This length here is x. So given a y value here, if I give you 0.9, you should be able to work out the radius. So hang on, if I give you 0.9 here, if I give you the y value, then you should be able to work out this radius. Once you've got the radius, then quickly pi r square it. That will then give you the area of the disk. Okay, so let's start again here. So the volume, hang on. So the volume is given by the integral from b, because we're doing it from b to 1. From b to 1. Pi r square it in terms of dy. But the thing is, we need to work out the radius. So what is the radius for a given? Let's say we're moving along like this. Let's say our tracker here is y. Our tracker here is y. We now need to work out this radius. So given y, we can work backwards to find the radius, which is x. So given a y, we need to make x a subject. So natural log both sides. That will then give us this. And then times minus 1, so that will then give you this. And then if you want x on its own, then square root the whole thing. Square root the whole thing. So what this is saying is that for given y, you can work out the radius, and the radius is given by this thing here. So it will be pi r squared, but the radius is this thing here. The radius is this thing here, so it would be square root minus natural log of y, and then we will need to square it, because it's pi r squared. This thing here is r, and then squared here is squared here. But then we can't call it the volume. Our aim is to work out the whole volume, but this is only from b to 1. So let's, instead of calling it v, let's call it the volume up to b, and then later on v equals when we take the limit as b heads towards 0 from the positive side. Okay, well anyway, the volume up to b is given by this thing here, by this thing here. So it's going to be pi r squared. That will then give you the area of the disk, and then you're summing up all the disks from b to 1, and you're moving in the y-axis, along the y-axis. So you're moving along in the y-axis. Okay, but then you might feel uneasy looking at this. Looking at this, you might feel uneasy of this negative here. You're square rooting a negative, and well, you've got this negative. You're square rooting a negative, so this might look uneasy here. This thing here. I will explain why it makes sense in the next video. Okay.